All right. I guess everyone can hear me well. So yes, I'm Pedro Holanda. I'm one of the main contributors of DuckDB, and I'm here today to tell you guys a little bit about it. I know another person talking about a new database system, but I hope I'll convince you guys that there was the need to build a new database system. And I'm going to be talking about how it actually interacts with the whole Python ecosystem. So that's the outline of our talk. I'm going to start a little bit with what is DuckDB. So just give you like a very brief motivation and what are the actual main characteristics, so the main design decisions we did there. Then I'm going to talk a little bit about the DuckDB in the Python land, do a very quick demo, 7 to 10 minutes. This demo is about estimating the New York City taxi fare costs with DuckDB and Pandas. So it's not really replacing Pandas. For those who saw the talk earlier, a lot of people trying to replace Pandas. We're not here to try to dethrone the king, but to work together to make it better. And at the end, like a short summary of the talk. All right, so what is DuckDB? So DuckDB was actually born at CWI, which is the Research Center of Mathematics and Informatics from Amsterdam. And in there, we're basically working, we're all like PhD students or researchers, and we're all working with data science projects that were from actual companies. And we quickly realized that in all these projects, no one's actually using database systems. They were all writing their own code to parse their CSV files or Parquet files, and start to use Pandas to do database operations. And we start to question ourselves as database researchers, OK, why is that the case? So, well, if you actually want to use a database system in a Python application or an analytical tool, you can do it by a database connection. So you have like your RDBMS. Probably if you're doing analytics, you're doing something like ClickHouse. And then for your database connection, you pass on the data to your Python application, and you do, I don't know, machine learning, data science, or whatnot. The problem here is that this becomes quite expensive because you have this transfer cost. So we thought, like, well, what if we can actually embed a database system inside the analytical tool, like SQLite does? Of course, SQLite is a database system that's catered for transactional workloads. So usually, you request one tuple, you update something on that tuple, not really for analytics, where you're getting like huge chunks of the data and performing some kind of aggregation or machine learning operation on top of it. So what if we can be the SQLites for analytics? And that's how DuckDB was born. So as you can see, DuckDB, the SQLite for analytics. Some of you probably heard this a couple times today already. And it's like, OK, we want to be like SQLites in the sense of it's simple to install. Like we want people to be pleased to use it, not have to start a whole server, to create a table schema, to then load their CSV files, or to transform their Parquet files there. We want simple stuff. So it needs to be simple to be installed. Just pip install DuckDB in Python, for example, and you're ready to go. Embedded, so you have no server management. Fast analytical processing, so really focused and catered for analytical workloads. And you need to have fast transfer between R, Python, and the database management system. DuckDB is currently actually pre-release as the version 0.6. And we say it's pre-release because our storage is still not consistent between versions. So in following versions, you basically have to reload all your data. You can check the website for more details. All right, so what are the characteristics I'm actually going to be talking about today? This is a little bit technical, but I promise I'll try to make it fun, or at least like engaging. So I'm going to talk a bit about columnar data storage, data compression, vectorized execution, end-to-end query optimization, automatic parallelism, and beyond memory execution. So columnar data storage, as you might know, there are basically two ways of storing your data. You can do it either as a row store or a column store. As a row store example, you have SQLites. And the thing about the row store is that your data is contiguously in memory per row, right? So you have the first row, second row, third row, so on and so forth. It means that individual rows can be fetched very cheaply because it's just a sequential part of your memory. However, if you fetch in only one column of your whole table, that also means that you're probably going to read your whole table. So in this example here, we have a couple columns, date, store, product, customer, price. And what if we only want to run a query where we're interested in the price of a product and not the stores in which it's sold, doesn't really matter. If we go for the whole column, we're going to fetch the whole table. And that's what column storage is for. Now you actually store the column continuously in memory, so you can fetch the columns individually. And this can cause immense savings on disk I/O and memory bandwidth when you have these typical analytical queries where you only get a few columns of your whole table. And as an example of column stores, we have Pandas and DuckDB. So to give you an example of what kind of savings we can have here, let's say we have a 1 terabyte table with 100 columns. And we just want to get 5 columns of the table, but the full columns. So in a row store, if you're reading this 1 terabyte with your disk going at 100 megabytes per second, that takes 3 hours. But in a column store, you suddenly don't have to read your whole table anymore. You can just fetch the columns you need. So to read these 5 columns is about 50 gigs. This goes to 8 minutes. So these are the main design difference that I want to show here from like something like SQLite or transactional database to analytical data management tools. The other thing we have in DuckDB is compression. So you can notice that individual columns, they often have very similar values. For example, if you have a time series database, you usually have dates. They are stored like increasingly, so instead of storing the actual dates, you can store their difference and save space there. Or if you have a lot of repeated values, you can apply RLE, which is basically saying if you have 6 tuples where the value is always 6, instead of storing 6, 6, 6, 6, 6, 6, you store, okay, 6 times 6. So it's just like simple compression techniques, but that can bring your data size to a very low value. And here I have an example of some of the DuckDB versions. So about a year and a half ago, at version 0.2.8, we had no compression. And today, we implemented a bunch of different things there: RLE, bitpacking, dictionary, double compression like FSST and chimp. And for very common benchmarks, so for example, the table from TPCA's line item or the famous taxi datasets, we managed to get already in a year and a half 3 to 5 times compression. So you can get a lot from this. And how does compression actually change in your execution? Well, again, if we go to the same example where we have 5 columns on the table, and you want to read these 5 columns, with no compression, you have to go 50 gigabytes. So that will take you 8 minutes. But compressing them with 5x, you can get to like 10 gigabytes, which already reduce your time even further, 1,040,000. And this compression can also go to the execution, but currently in DuckDB is only really in our storage. What about execution? Well, SQLite uses tuple-at-a-time processing, which means that when you have your query plan, you have 1 tuple going through each operator up to your results. Pandas uses what we call column-at-a-time processing, which basically means you process the whole column on each operator of your plan. And DuckDB uses vectorized processing, which is kind of a mix. You don't really do 1 tuple, you don't really do 1 column, you do a batch. And this batch has a magic number there, which is 2048 elements. And that's what you go passing up to the top of your plan. So OK, so tuple-at-a-time or SQLite, it's actually optimized for low memory footprints. It comes from a time that memory was very expensive, and your data probably didn't fit completely in memory. And it's very nice because you actually only have to keep 1 single row in memory. However, for analytics, it's quite costly because it adds a lot of overhead on your CPU. So every tuple that's going on in your plan, you have a function call, gets your query quite expensive. Pandas, doing the column at a time, it actually presents a better CPU utilization. It allows for SIMD, but has one big issue, which is you actually have to materialize your whole column at each operator of your query. So you end up materializing large intermediates in memory. These intermediates can be gigabytes each, and this becomes quite problematic when data sizes are large. I guess a lot of people are faced this issue where your data just does not fit in memory. Pandas is like, OK, I give up. And then Vectorize is what DuckDB does. As said, this is optimized for CPU cache locality. It still allows for SIMD instructions and pipelining. And the whole idea is that you actually have your intermediates. That's also why you have this 2048 number, is that they actually can fit on L1. So basically, I'm not sure how familiar you guys are with modern CPUs, but basically you have a CPU core, and you have these L1, L2, L3 caches in the main memory. The bigger it gets, the more expensive it gets to access data. So if your data fits on L1 cache, you're processing the whole query plan, paying only latency of 1 nanosecond. But again, in the example of Pandas, if you have your whole data fitting in main memory, it means that every time you go in there, you're paying the latency of 100 nanoseconds. And it starts to accumulate, and it presents a huge bottleneck on query processing. End-to-end query optimization. Yeah, so in DuckDB, as a good database management system, we have an optimizer. That means your expressions can be optimized. That means join ordering. If you have multiple joins, they are going to be reordered to start processing from where you have the least amount of tuples. We have subquery flattening. So instead of having subqueries executing where you have a bunch of function calls every time that you want to execute subquery, you actually can transform it to a join. And we even have filter and projection pushdown, which is actually a pretty basic optimization, but it's one that Pandas does not do. So just to showcase what a projection pushdown would be, here we have a table with just 5 columns, A, B, C, D, E, right? And then we have our query there, which is just getting the minimum of A, where A is higher than 0 grouped by B. So that means that to run this query, you only need 2 columns, A and B. So you can see here in Pandas that you actually, in DuckDB, that you actually push down these 2 columns to the scan. So that means that these columns are the only things you're reading. But in Pandas, unless you set it up initially and manually, that means that when you go to the filter df there, where you're just getting all the tuples that are higher than 0, you're still scanning the whole table. So simple query optimizations, they come for free in DuckDB. Automatic parallelism and beyond memory execution. So DuckDB has parallel version of most of its operators. I'd like to say it all, but I'll go with most. Scanners, so all the scanners or data scanners, they are parallelized, and they have the option of preserving insertion order, aggregations, joins, and as you might have heard, Pandas, of course, can only support single-threaded execution. And DuckDB also supports execution of data that does not fit in memory. So our main goal is to never crash. We never give up. We never surrender. We're going to execute whatever query the user might throw at us, even if it doesn't fit in memory. We try to have graceful degradation, so there's suddenly not a huge cost for the query that when it not fits, and never crashing. All right, DuckDB in the Python land. So DuckDB has mainly 2 APIs. It has a Python DBI API, it's Python DBI API compliance, which means that you can create connections, get cursors, executes, fetch all, fetch many, fetch one, everything that's defined there. And we also have a relational API. The idea of the relational API is that you have something that's somewhat familiar to Pandas. It's not a one-to-one mapping, but you can say like, OK, you can get, for example, here we have our database, and it has a table called integers. So you can use DuckDB.table to get that relation. And then that relation, you can, for example, use show to print what's in there. It actually prints with a limit, so just so that you have a feeling. And you can also chain multiple operators, very similar to Pandas. So you can chain like a filter, a projection, and then do prints. Integration. So we have a lot of, I would say, very tight integrations with different Python libraries. And with tight, I mean they are zero copy. Not always, but most of the times. For inputs and outputs. So for example, for Pandas, in the code example here, we have a data frame, 2 columns. We create a connection, DuckDB, and then we can actually select the elements from the data frame. So we can run a query, select star from df. df is the name of the data frame. And we can actually scan the values there without copying it. And we can get the results from this query, which should be the data frame values again. But we can export it to a data frame as well. Again, zero copy. So we can interact with data frames without paying any huge costs in it. The same thing with PyArrow. So we do the same with Arrow. Very similar example to the Pandas one. We can just select from arrow objects, arrow tables, arrow streams, and we can also produce them. We have the same with NumPy. We also are integrated with SQL Alchemy, and we are integrated with IBIS to the point that it actually became, I think recently, their default backends. A bit of usage. So as you can tell, last month we had about 640,000 downloads in our Python API. Daily, about 32,000 downloads. So these numbers have been increasing quite fast, but we are growing in terms of how many downloads we get in our Python package and how much used it is, exactly because of these integrations we have. All right, now it's time for a quick demo. Let me make this bigger. Can you guys from the back see it? I hear, yes. OK, I see a yes. All right, so this demo as well was going to be pretty simple. So here is just showing like, OK, install DuckDB is just a pip install. This pre here is just to get like the latest version. And then we get like our data set, which is a Parquet file with the New York City cab data sets for the January of 2016. We import our libraries. We're going to be using Pandas, some timing library in DuckDB. And we can just load the data with Pandas. So to load the data in Pandas, this is a Parquet file. We can just use read Parquet, and we get our data frame. Takes a little of a while here. Yeah. All right. Here we just have like a very simple time function. Nothing too fancy here. It just runs 5 times, gets the mean value. And then we're basically going to be calling this guy for all the queries we're going to be running during the demo. So here, the goal we have here first is like, OK, let's pretend we have this question. Like, OK, we have all this information about cab rides. Does the average tip value actually increase the more passengers we have for short trips? So the more people we have in the car, higher the tip or not? And then to answer that question in DuckDB, of course, you can just use SQL. You can get the passenger count, an average of tip amounts. You can scan exactly from the data frame. So you just have to pass the data frame name here, set your where clause, OK, where the distance is lower than 5, and you group by the passenger counts. And again, the nice thing of this is that you can also return a data frame here. And why would it be interesting to return a data frame? Well, Pandas actually has this very nice integration, for example, with plotting. So since we got a result of data frame here, we can just call plot bar, and then immediately get like a nice figure about it. So what we can see here is that there's probably some dirty data there because there's 0 passenger counts, or maybe, and somehow they're also getting tips. I'm not sure if that's how it works. But otherwise, apparently, after 8 passengers, which I guess you probably get like some kind of minivan, your tip value increases there. So there is, to a certain number, some correlation to how much money you get from your tips for short distances. And again, doing the same thing in Pandas would actually be, OK, we want to filter the data frame, get all the travels that had a distance lower than 5, group by the passenger count, and get the mean value of the tip. And then basically we do the same here like we do the plots. And like what I want to showcase here is actually the difference in timing. And keep in mind, this is a small data set. And this, I think the Colab machine has like 2 cores. So the parallelism here, it's also not that big. But DuckDB, we run this query in 0.26 seconds. And then if we go to Pandas, is 1.37. So even for not such a complex query, small data sets, not a beefy machine, there's already like quite a big difference. And that's, again, not really exploiting as well out of core execution. Pandas will just crash there, unless, of course, you do some manual handling. And then I also have an example like, OK, you're showing me something that's not really data science-y. Let's do something a bit more fancy. Can we do estimate fair with the linear regression in DuckDB? So how much the distance of the trip will actually affect. So I'm not going to go into the details of this query. but the square is basically calculating the alpha and beta for our regression. And I really just want to show you that this is actually possible to be executed as well. So here we present like our alpha is 4.65, beta 2.66. And then again, you can just output a data frame for this and actually plot it very nicely. So there you go. We have our linear regression. And again, just as confirmation, I can do the same in Pandas. Also, this time just calculating the alpha and the beta, and that's the only thing that I'm actually timing it here. And we can see that it's going to take a little longer than in DuckDB. Little longer. Yeah, all right, 2.18. So the time here, you can check the alpha and the beta is the same, right? The data is the same, so 4.66. Here was also 4.65, 4.65, 2.66, 2.66. The time here is 0.7 seconds, and in Pandas, that's 2.1. So yeah, that's a 3x difference. Again, query now is a little bit more complex, but it still is really not stressing out the full potential because of the machine. But you can already see there's like a noticeable difference there. All right, that's going to be my last slides. So a bit of a summary. Yeah, so DuckDB is an embedded database system. It's designed for analytical queries, so it's really catered for data analysis, data science. It's completely open source under MIT license, which is the most permissive license there is, and free to use. So if you download it, you basically get the max out of DuckDB. Has binding for many languages, Python, R, Java, JavaScript. Like, well, if there's a language, you probably have a binding for it now, I think. Tightly integrated with the Python ecosystem, so zero copy access to Python, NumPy, PyArrow datasets. Implements the DBI and relational APIs, and has full SQL support. And that's something that I really want to stress. I know data scientists love their chaining operators, but SQL is cool. We fully support it. You can just run SQL on data frames. I think that's very nice. That's it from my side. Yeah, and I'll be very happy to take any questions if you guys have them. Thank you very much for paying attention.
No, I don't even have to throw.
Thanks for the talk. Looks very interesting. I'm definitely going to check it out. So does it support user-defined functions in the execution engine?
Yes, it does support user-defined functions. I mean, you can implement them in C++, but yeah, not in Python, for example. So yeah, as long as it's the same language as the core, you can implement them there.
Yeah, but I mean, in Pandas, you can simply write a Python function that does some kind of manipulation of a column that might not be easily expressible in SQL. So can you? I mean,
but that's also what's very powerful about it, right? Since you can actually get your data, for example, as a data frame, you can also exploit things or operations that might exist in data frames already that might not exist in DuckDB. So it's also easy to integrate with them. And again, that's also like the thing why it's integration is like using the best that Pandas has to offer, which is years and years and years of development, but it's still like keeping the fast core execution where necessary.
Yeah, cool, thanks.
Anyone else? Maybe all the way in the back to give me some extra steps. There we go.
That's a good exercise, I guess.
Yeah.
So, first of all, thanks for the talk. It was very interesting. But we were mentioning a lot of speed. How does it compare with the faster bear on the block? In this case, polars.
That's a good question. Mark, do you have benchmarks against polars?
Yeah, we ran the H2AI. It's very comparable. I think in complex queries we're usually faster. On aggregations it's the same, but it's same ballpark.
Yeah, okay, so I'll just repeat Mark's answer. It's same ballpark as polars, regressions are comparable, but I think the main difference there is that we do support a wider range of operators. So for example, if you try to run TPCH, classical analytical benchmark on polars, it won't be able to run all the queries because I think polars don't support subqueries, for example. Also, like out of memory execution, polars has some support to it if they are streaming queries. We fully support it. So it is performance, but also usability to a different range of cases.
Any more takers for the cube?
I'm glad I didn't walk all the way back down.
What I was interested in, I think SQLite was meant as a local development database for example, building applications. Well, DuckDB could do it for analytical purposes, but when you then go to production, you often shift the database engine with something that can scale even further. Is that also the purpose for DuckDB, or should you run DuckDB also in production then?
In production, you scale even further. So you mean like going to the cloud, classical data warehouse scenario, or?
Yeah, exactly.
So the current purpose of DuckDB right now is to be something that actually exploits your full capacity on your laptop. So it's not meant to be a distributed database system. We do have a partner company that's trying to do exactly that, but it's in the sense of, OK, your data starts to grow. You cannot execute your queries on your computer anymore. So the name of the company is Mother Duck, before I forget to mention. They call themselves the Mother Duckers, so very nice people. But then it's like, OK, if it doesn't support your laptop, you can actually seamlessly grow to cloud environment at some point. But currently, it's really focused on getting the max out of the desktop, laptop, single nodes.
Yeah, OK, clear. Thank you.
Are there any other questions?
Well, this is your chance to make me walk again.
Ah, there, in the back.
Oh.
So thanks for the talk. A quick question regarding the design when it comes to like exceeding the memory available. I assume that by default you spill to disk, but is there a way to actually force the failure of the database and say, OK, if you have, like, for example, very strong resource limitations, can you rely on stuff like C groups, or do you have some internal settings to force the failure if you don't have enough memory to avoid spilling to disk, basically?
I don't think we have a way of forcing failure because you don't have enough memory. Oh, we do. OK. Thanks, Mark. But
okay,
you can set the memory limit, but does this cause a failure?
That's in the pragmas, right?
Yeah.
Okay.
For the pragmas.
Would you mind joining him on
Yeah,
that?
sure.
Thank
Yeah, sorry. Yeah, you can set the memory limit, and basically you need to specify a location on disk to spill to. If you don't specify that, then it won't be able to spill, and then it will fail.
Okay. Thanks.
But our queries are also, you can also cancel them if you wish, so. It's also an option.
So we have time for one more question. Does anyone have
One more?
one more?
Otherwise, I will come up with one more.
Yeah. Thank you, random person that I don't know. So, as you guys might know, we actually come from the far, far away land of Amsterdam. Woo! And we did have to bring, for you guys, all of you here, mugs and hats. And mugs are heavy, so we brought them. We don't want to bring them back. Please, if you don't have a mug and a cap and a bottle opener yet, pass by our booth, get some of our merch. We really brought it for you guys, so don't make us bring it back.